object, then it is a device which is going to couple, which is going to join two parts of the shafts. Okay, either that part may be a part of prime mover, or that shaft may be part of the machine where you want to join that prime mover. Basically, couplings are used to join a prime mover with the machinery. That is appropriate thing. That means when we are going to join IC engine with centrifugal pump, then we are going to use coupling in between that. Okay. So, and other thing is that when we are going to transmit power through a long shaft, at that time, the shaft to prepare the long shaft, it is not durable or it is not possible sometimes. Then we are going to couple that two parts of the shaft. Okay. It is for the power transmission. But basically, more or the less, you can say that the coupling is used to connect the prime mover. Prime mover, that is nothing but the power source, okay, where the power is generated, that with the machinery. So that is a what we can say coupling is. Okay. Now the coupling of requirements of good coupling, that means how that coupling should be, that we'll see one by one. Now what it should possess, it should be easy to connect and disconnect. That means the coupling which we are going to design, basically if you are going to start our design from the conceptual design, that is nothing but if you are going to put a new concept for that, then you put your concept in such a way that that particular assembly of coupling, that is nothing but when we are going to join it together, it should be easy, okay, to connect, and it should be easy to disconnect also. It should transmit the full power from one shaft to another shaft. That means it should not consume any power, it should not waste any power. The coupling should not waste any power. Okay, it should hold the shaft in perfect alignment. That means sometimes due to coupling, misalignment occurs in the machinery, and that misalignment leads to severe problems of that machinery. So it should be perfectly aligned. Okay, if you see the couplings, then most of the times the problem is of misalignment in case of coupling. So your design, your coupling which you are going to design, that should be perfectly aligned. Okay, it should reduce transmission of shock loads from one shaft to another shaft. That means it should not provide the jerk. It should transmit smooth power from one shaft to another shaft. Okay, so that the vibrations will not be generated in that machinery, and further we will not have any problem. Okay, it should have no projections or projecting parts. One more we can add in that, that it should not have any loose part, because when we are going to couple two shafts together with the help of coupling, that coupling is also going to rotate with the high speed. Suppose we consider that motor is connected to the pump, then that motor is going to run with 1440 rpm. At that time, mr omega square, that will be the force which will be generated, that is centrifugal force. That's why this omega is going to double. Okay, so it is going to come in square, and m very small part, if suppose is going leave from that coupling, that is nothing but if it is loose, and if it comes out from the coupling, then that mr radius at which it is rotating and omega square, that much force will be generated. And anybody who is working besides that, that may hamper, or that part may hamper to that person, human being, or any other machinery which is beside to that. So it should not have any loose part, and it should not have any projecting parts. Why? Because the projecting parts should not be there, because it is rotating with very high speed. Okay, these are some requirements of good coupling, and existing couplings are meeting that all requirements. Okay, there is again possibility that you can have any new invention in that. Okay, now we are going to see types of couplings, so the shafts which are connected with each other. So they are broadly divided as flexible coupling and rigid coupling. Out of that, we are going to see the rigid couplings. Okay, flexible couplings are not involved in our syllabus, so we are going to concentrate more on the rigid coupling. But as we are going to see the types, there are two types. One is called as rigid coupling and another one is called as flexible coupling. Okay. So what the rigid coupling is, it is used to connect two shafts which are perfectly aligned with each other. Okay. And following type of rigid couplings are used. One is called as sleeve coupling, then clamp. Okay. That is split muff coupling. Okay. And flange coupling. Out of that, again, this flange or this muff coupling. Okay. It is split type of muff coupling. Okay, that is also not included in syllabus, but sleeve type and this flexible coupling, sorry, flange coupling. These are the two main parts, okay, of our study. Next is flexible coupling. In case of flexible coupling, it doesn't mean that it is flexible and is not capable to transmit the power. Okay, but it is used to connect the two shafts, both lateral and angular misalignment. Okay, that is, it is allowed to have the angular and lateral misalignment. That's why it is called as flexible coupling. For example, if you are going to take example of power transmitted from what we can say engine to rear wheel of the truck, you might have seen that propeller shaft is going to rotate. In between that, again, one coupling is used. Okay, universal joint it is called as. It is also coupling. Okay, but some align that misalignment is allowed in that. That is, angular misalignment is possible in that case. Other example we can take, if you see the flexible spring type of couplings are used, where power is transmitted, torque is transmitted, but angular misalignment in that two shafts is allowed. Okay. Another is called as rubber type of bush type of couplings are there, where again in between two couplings flange, one rubber bush is used, and that bush is allowed to have some sort of misalignment, that is lateral and angular misalignment. Okay, so these are called as the flexible coupling. So example of that flexible couplings are mentioned over here: bush type of, okay, bush pin type of coupling, universal coupling, Oldham's coupling. These are the examples of flexible couplings. Okay. So out of that, we are going to see first that sleeve or muff coupling. Now here you can see the diagram of this sleeve or muff coupling. Okay. What is it includes? It includes one bush or hollow type of shaft, you can say, having length L, and is inserted in one shaft. Okay. And later on, that another shaft is also inserted in that bush or muff, it is called as. And in between that muff and these two shafts, one key is inserted. Okay, normally jib headed key or any other square or rectangular key is also used in that case, but jib headed key is preferable because it is easy to dismantle. So this key is used and these two shafts are connected with each other. In this case, the shaft should be perfectly aligned. Any type of misalignment is not allowed in this type of coupling. And simply on these two shafts with the length L, this muff is going to cover that part of shaft. Okay, and that is called as muff coupling. It is very simplest form of coupling where we are going to connect two shafts with each other and power is transmitted with the help of that coupling. Okay, in this case, the outer diameter, okay, these are the thumb rules. We can say again, is it visible? Screen is visible or not?
Yes,
Hello?
sir, it is visible.
Okay, okay, very good. So when we are going to use these type of couplings, okay, then as we have seen, there is some standardization in the design. So outer diameter of sleeve is normally taken as a twice of shaft diameter plus 13 mm. Okay, this, you can ask me question that from where this 13 mm is coming. Okay, it is just allowed, or you can say additional thickness which has been provided to the sleeve or muff. Okay, so this is standard, and as the diameter of shaft is going to change, the outer diameter of this sleeve will get changed, or outer diameter of this muff will get changed. So here in this diagram, Capital D we are used for the outer diameter. Small d we are used for the shaft diameter, and that will become the same as the inner diameter of this muff. Okay. And normally length of this sleeve or muff is taken as a 3.5 times of D. Okay, that is the 3.5 times of shaft diameter, and that is capable to sustain the torque which we have to transmit. Okay, this is what we can say general discussion about the this sleeve or muff coupling. Next, if we are going to design that sleeve or muff coupling, okay, then what it includes? First of all, we have to design this sleeve that is nothing but muff. Okay, so in case of sleeve is designed by considering the hollow shaft theory. Hollow shaft theory, that is nothing but as we are going to design the shaft, already we have seen what is the procedure for the designing of that shaft. So torque which is transmitted by means of shaft is given by pi by 16 tau c, where tau is the shear stress, that is design shear stress, which we can calculate from the given shear stress, or we can calculate it from the yield strength of that material, right? So T is the torque which is transmitted, and tau C is the permissible shear stress in the material for that sleeve. Normally, which is manufactured from the cast iron. Okay, and the shaft value of the shear stress for the cast iron is normally taken as a 14 megapascal. Now this 14 megapascal, don't worry about it because it will be provided in our problem statement. So what allowable shear stress we have to take, we don't have to worry about it. It will be provided in the problem statement. Now in this case, if you are going to design hollow shaft, we know that the torque which is transmitted is given by pi by 16 shear stress, allowable or design shear stress, into bracket capital D raised to 4, where capital D is the outer diameter of sleeve, minus D small d raised to 4, where small d is the diameter of shaft or inner diameter of that sleeve, divided by D, capital D, that is outer diameter, and that is given by pi by 16 shear stress multiplied by D cube into bracket 1 minus K raised to 4 should not be there. It should be K raised to 3, where K is the yeah, it is right. K raised to 4 should be there because this D is divided and here it is cancelled by means of 1D. If you are going to take this 4D as a common or capital D as a common, right? So K is nothing but the small d, that is shaft diameter, divided by the outer diameter of that muff. Any question? From this expression, we can calculate the shear stress and we can design or we can calculate the dimensions of the sleeve. Okay. The next is design of key. As we know that key is designed. Previously, we have designed that key. Okay. Same procedure is followed and the key is designed. So these two are the main parts of this muff coupling. That is sleeve. It should have dimension capital D and small d, and key which we have designed in the previous part. So in that case, the standardization is used. Normally length of this key, because when we are going to design key for the transmitting the torque T, at that time we also calculate the length. But here in this muff coupling, at least this key should be having dimension equal to the dimension of that sleeve, length of that sleeve. Okay, and this length of sleeve, okay, is basically taken as a basic for calculating the length of this key. It should be more than that. Okay, at least it should be equal to the length, but normally it is taken more than that. So this length of key is taken as a L by 2. Okay, and this L is calculated as 3.5 times diameter. Already we have seen in the very first slide. Okay. So once you calculate that length of that key, then thickness and all that we have to, width and thickness, that we have to calculate as we have seen in the yesterday's lecture. Okay. Where this calculation, dimensions calculations for the keys are given as a transmitting torque is equal to L multiplied by B, okay, multiplied by tau. Tau is the allowable shear stress in key material. Okay, it is not a allowable shear stress in muff material or shaft material. It is allowable shear stress in key material multiplied by small d by 2, where small d is the diameter of that shaft. Okay, if we are going to consider it in shearing. If we are going to consider it in crushing, just replace this shear stress by means of this crushing stress. Okay, rest of that formula will remain as it is. Okay, as we have seen in designing of that key. Okay, these two formulas are there, and we can equate it for the square key. And as you know that the shear stress is twice of that crushing stress if we are going to use the square key. Okay. Any doubt related to this MUP coupling design? Hello? Hello? Can you answer me?
No, sir.
Okay. Then we'll see one problem of this MUP coupling design. The problem statement is design a MUP coupling which is used to connect two steel shafts transmitting 40 kilowatt at 350 rpm. Okay, power is given, rpm is given, we can calculate torque. The material for the shaft and key is plain carbon steel, for which allowable shear and crushing stress may be taken as 40 megapascal and 80 megapascal respectively. Okay, shear stress is 40 megapascal and crushing stress, that is compressive stress, is 80 megapascal. The material for the muff is cast iron, for which the allowable shear stress may be assumed as a 15 megapascal. Now in this problem, power which has to be transmitted by means of that coupling is given, that is 40 kilowatt, that is 40 into 10 raised to 3 watt. Now we have to convert it into watt because all dimensions we are going to take in millimeter and Newton, or we are taking in Newton only. Okay, so this will become 14 to 10 raised to 3 watt. Then speed is given as a 350 rpm. Then shear stress, for the allowable shear stress for shaft material and key material is given as a 40 megapascal. Okay, that is 40 Newton per millimeter square. Then this crushing stress is given as 80 megapascal. Okay, that is 80 Newton per millimeter square. And shear stress for the key coupling, that C suffix is used for the coupling. Okay, then shear stress for the coupling is given as a 15 megapascal, that is 15 Newton per millimeter square. Okay, now we have to design this coupling. Now we know that first of all, we are not knowing the dimension of shaft here. So we'll use the basic equation by means of which we can calculate the shaft diameter. Then afterwards that will become inner diameter of that muff, and we have to find out the outer diameter of that muff. Okay, which is normally equal to double of that shaft diameter plus 13 millimeter. But we are not going to make that calculation. We are going to check it whether it is sustaining that shear stress while transmitting the torque. Okay, that's why that shear stress equation has to be used. So let us consider that small d is the diameter of that shaft. Okay, and later on we'll calculate the torque which is transmitted by means of key and muff. Okay, First of all, we will calculate how much torque has to be transmitted because torque is not given in the problem statement. So we know that P is equal to 2 pi nt upon 60. From that, we can derive this equation that T is equal to P multiplied by 60 divided by 2 pi n, where P is power, n is the speed. So power is given as a 14 to 10 raised to 3 watt, and speed is given as a 350 rpm. So from that, we can calculate the torque which is transmitted, that is 1100 Newton meter. That will be the torque which is transmitted, right? Now, I'm saying here it is Newton meter because here we are going to use that value in watt. Okay, that's why it will come in Newton meter. So while calculating it, so you take care of that dimension, that unit which we are going to use. Okay, as well as the dimensions which are given in the problem statement. So concentrate on unit. So this torque which is transmitted is coming as a 1100 Newton meter. We will convert it into Newton millimeter because all dimensions, that is stress which is induced, its limit is given in Newton per millimeter square. That's why it will convert it into Newton millimeter. And it will be 1100 into 10 raised to 3 Newton millimeter. That much torque has to be transmitted by means of that shaft, key, and muff. Okay. So this torque which is we are transmitting with the shaft equation, we know that T is equal to pi by 16 allowable shear stress into D cube. So from this we can calculate the value of D, that is shaft diameter. We are knowing here what the pi is, what the shear stress is, allowable shear stress is. Okay, it is 40 into 10 raised to 3, and this 1100 into 10 raised to 3, that much torque is transmitted. Okay, so 40 Newton per millimeter square, that is the allowable shear stress. That value we are going to put here, and we are going to get this equation as 7.86 d cube. Hence we can solve it for the d, and we are getting diameter as 52 millimeter. Okay, you can assume it as a 55 millimeter, or you can take as it is, that is 52 millimeter, for the further calculation. Okay, it's better to select next available value. Okay, it may be 54 or it may be 55. So we'll consider here. Again, I'm going to repeat it. That is up to you. But don't consider any value below the value which you have calculated. We cannot go for 50 millimeters, say approximately it is 50 millimeter, and we have calculated it as a 52. Definitely it will get fail, right? So don't select any value below the value which you have calculated. Select that value above the value which you have calculated. Here we will consider it as a 55 millimeter. That is the diameter of that shaft, and same is the inner diameter of that sleeve. So when we are going to design the sleeve, we know that the outer diameter of sleeve is the twice of the inner diameter plus 13 millimeter. So roughly we'll calculate it, and it is coming as a 123 millimeter. We'll consider it as a 125 millimeter. Okay, and length as 3.5 times of the diameter of that shaft or inner diameter of sleeve. So length we have calculated as a 192.5 millimeter. So we'll roughly convert it into 195 millimeter. Okay. Now these dimensions we have calculated of the sleeve, but we should check whether that sleeve is capable to sustain that torque. Okay, and that can be considered by considering the failure of that sleeve in shear. Okay, and this shear failure we are going to consider that as a hollow shaft. So the permissible shear stress which is given as a 15 Newton per millimeter square. Okay, and if we are going to calculate it by means of the torque which is transmitted in hollow shaft, okay, that is coming below 15 Newton per millimeter square, and hence we can consider that the design is safe. Okay, any question related to this? How we can check it? Okay, that you can ask question. How you can check that as we are going to say that it is safe, but whether it is safe or not. Do you have a calculator with you? Hello, anybody of you have calculator?
Yes, sir.
Okay, so you do calculations by using this formula. So put value of T, value of inner and outer diameter, okay, and you just calculate what value of tau we are going to get in this. So put this T as 1100 into 10 raised to 3, then this capital D as a 125 millimeter, small d as a 55 millimeter, and you just check it for tau. How much value of tau you are getting? मी काय म्हटलं या सर कळालं ना?
Yes, sir. Yes, sir.
Okay, just calculate and give me answer what tau you are getting. Yes. Anybody else do a calculator? You also can calculate. काय करायचं या सर 1100 into 10 raised to 3 multiplied by 16 divided by pi divided by 125 cube divided by 1 minus k, that is nothing but 55 divided by 125 raised to 4.
Tau ची व्हॅल्यू ते 2.98.
2.98, which is well below than the allowable shear stress. Okay, so we can say that the design is safe. Okay, next we are going to see flange coupling. Now muff coupling is over. We are going to see flange coupling. In case of flange coupling, as we are going to see in the diagram, flanges are provided on the two mating shafts. In this type of coupling also, the alignment should be perfect. Any misalignment is not allowed in this coupling. Okay, so first of all, we have to align these two shafts completely, and then afterwards we can join these two shafts with the help of flange and the fasteners, that is nut and bolt, which are provided on that flange. Okay, in this case also this coupling is usually used to join primor to the machinery. Okay, daily life example, you can say that in centrifugal pump, water pump, motor is connected with the pump by means of this coupling. Okay, nowadays monoblock pump set is available. That is nothing but only one shaft is used in between pump as well as motor. It's called as monoblock. No coupling is required in that case. Okay. But if you see the old type of centrifugal pumps, then the coupling is required in that case. Okay, but if you see the large capacity pumps, then nowadays also they are not available in monoblock type. They are available separately. Pump is manufactured separately and motor is manufactured separately, and two shafts are connected by means of this flange. Okay, also you might have seen in industry also various type of machineries are connected with the help of with prime mover by means of this coupling. Okay, so this flanges are manufactured from the cast iron normally. Okay, and shaft, as you know, that they are machined one, and these fasteners are used as standard fasteners, standard dimensions fasteners. Okay, nut and bolt. Here you can use that we can tapered bolt also, where the assembly and disassembly will become easy. But normally, this hexagonal bolts are used in this case. Now here, with the help of this diagram, we will understand that the small d is the diameter of shaft. Okay, both shafts are having same diameter, and small d is the convention which is used for that. Then flange is connected by to the shaft by means of key. Okay, so we'll consider this key dimensions of key later on. A small d1 is the diameter of the bolt which is used for the fastening. Okay, then capital D is diameter of hub of that coupling of that flange, because flange has an inner diameter and outer diameter also, and some part is projected so that the nut and bolt can be fixed on that flange. Okay, so flange hub, which is, we can say, diameter of that flange hub minus diameter of the shaft is nothing but the thickness of that flange. Okay, so this hub diameter we are going to consider as a capital D, which is taken as a twice of the inner diameter of that flange or inner diameter of that hub. Okay, that is the shaft diameter. Then D1 is taken as a diameter as at which the bolts are fixed. Okay, that is pitch diameter, we can say pitch diameter of the bolts, that is denoted by means of capital D suffix 1. Okay, and which is taken as a thrice of shaft diameter. Then outer diameter of the flange is denoted by means of D2, capital D suffix 2. Okay, which is taken as a 4 times of the shaft diameter. Okay, these are the all diameter which are in the flange coupling and the conventions which we are going to use in the flange coupling. Now we'll think about the thickness of this hub as well as this flange. Okay, T suffix F is considered as the thickness of flange. Okay, and this L is considered as a L. Here the L is only considered up to this. From this point to this point only. Okay, can you see it? Is it visible? So that is called as flange length, and which is taken as a 1.5 times of the shaft diameter. The total length of this coupling will become L plus one more L. Okay, 2L it will become. So 2L is the length of total coupling. Getting me? Or total length of this hub. So for single, it is L, it is considered as a L, and which is taken as a 1.5 times of the shaft diameter. Okay. Is there any question? Here it is explained the same. That is, D is taken as a twice. Capital D, outer diameter of hub is taken as a twice of the inner diameter of our shaft diameter. Length is taken as a 1.5 D of that hub. Then D1 is the diameter at which the bolts are mounted. Okay, that is pitch diameter of bolts, and which is taken as a thrice of D. Then outer diameter of the flange is denoted by D2. Okay, and it is equal to D1 plus D1 minus capital D, and which is taken as a 4 times of the shaft diameter. Okay, then thickness of flange is taken as a half of the shaft diameter. Now this I have not mentioned in the diagram. Okay, This is taken as a half of the shaft diameter. Now, the number of bolts which are used for the connect, this is again the standard values. Okay. Number of bolts which are used for connecting these flange are 3 up to 40 millimeter shaft diameter. And we have to increase number of bolts to 4 if you are going to use shaft from 40 to 100 millimeter diameter. And if the shaft diameter is more than that, up to 180 millimeter diameter, then 6 bolts are used. And you might have seen that very big shafts are used in case of turbine, in power generation for the water turbine or for the steam turbine, shaft which is used having diameter more than 180 millimeter. Then in that case, we have to calculate number of bolts which are used or which are required. Okay. And they are varying from 10 to 20 also. That is depend upon what is the diameter of shaft and how much torque you are going to transmit. Okay. Any question? Next, the coupling which we have seen is the unprotected type coupling. Unprotected means the projected part is not there on this flange. Okay, so it is called as unprotected type flange coupling. And next, what we are going to see is the protected type flange coupling. Now, this protected type flange coupling, that is nothing but only this cap is provided on the flange. Okay, so that this nut will get protected. If it is loose, it will not come out of the coupling. Okay, so that's why this nut and bolt is protected. That's why it is called as protected type of coupling. Okay, due to centrifugal force, it will not come out. That's why it is called as protected. It will thrown to other side. Okay. In this case, only one dimension will get changed, and that is the thickness of this protected cap. Okay, that is called as TP. T suffix P we are going to use. That we will see how to calculate that TP. It is also 0.5 of shaft diameter. That is equal to the thickness of that flange. Rest of all dimensions are as in case of unprotected type flange coupling. Now we'll see the procedure by means of which these flanges are designed or this flange coupling is designed. First of all, we'll consider that the small d is the diameter of hub or diameter of shaft, inner diameter of hub or diameter of shaft. Capital D is the outer diameter of hub. D1 is the normal or outside diameter of the bolt, small d1. Capital D1 is the diameter of bolt circle, that is each circle diameter of bolts. Then N is the number of bolts which are used. Then T suffix F is the thickness of flange. Tau S is allowable shear stress. Tau B is the allowable shear stress in bolt. And tau K is the allowable shear stress in key. Okay. Tau S is allowable shear stress in shaft. B in bolt and K in key. Tau C is allowable shear stress in coupling, flange. Okay, flange material. Normally it is cast iron. Sigma C, sigma suffix CB is the allowable crushing stress in bolt, and allowable crushing stress in key is denoted by sigma suffix CK. Okay. These are the nomenclatures which we are going to use. Now, step by step, we'll see how this coupling is designed. First, we have to design hub. Now, hub is designed by considering it as a hollow shaft. Okay. And this already we have seen the formulae by means of which torque which is transmitted in that hollow shaft is given by T, the torque which is transmitted, is equal to pi by 16 allowable shear stress in that coupling into d raised to 4, that is capital outer diameter raised to 4 minus inner diameter raised to 4 divided by d. This again can be simplified to pi by 16 Tc into capital D raised to 3 into bracket 1 minus k raised to 4, where k is small d divided by capital D. Okay. This is the torque which is transmitted by means of that hub of flange. Now the outer diameter of hub is usually taken as a twice of the diameter of shaft. Therefore, from the above relation, we can just check whether the shear stress is within the limit or not. Now the length of hub is taken as a 1.5 times of the shaft diameter. Okay, that length we have used as it is. Then design of key. Key has to be designed as we have seen in yesterday's lecture. How to design that key, how to calculate its width, thickness, as well as length. Okay. Then design of flange. Once this hub is over, then the remaining part of that flange coupling, that is called as flange, that we have to check. Now this flange is again considered for transmitting the same amount of torque. Okay. And while transmitting this torque, what we are going to consider, circumference of that hub, that is this circumference. Okay, from here, I'll take this diagram. Okay, let it be of protected type here. Now, this hub is okay capable to transmit the torque, but what will happen at the junction here? Here it may get failed, right? Here it may get shear out. Can you see it at this junction? So how much torque is available at this junction, that we have to calculate. That's why we are going to take this capital D for calculating the torque. Okay. Again, where the flange is connected to hub, at this place, it may be possible that it will get shear out. Okay. At total periphery. That's why we are going to take this capital D as a diameter of the hub. Okay, for calculation. Now the circumference of hub, which is going to get shear out, that is area we are going to calculate, plus multiplied by thickness of that flange. Okay, this thickness of flange, that is nothing but area which is undergoing for the shear, multiplied by shear stress, allowable shear stress in the flange, multiplied by radius of the hub. Now how these two are taken? This is the basic equation, that is shear stress tau is equal to force divided by area. And while we are going to calculate the force from torque, it is nothing but torque divided by radius. That's why this radius we have taken at this side. Then shear stress and area. Okay, stress is equal to force upon area. So force will become stress multiplied by area. And to calculate force, if you are going to take this radius to this side, torque divided by radius is nothing but force. Okay. So just this equation has converted from the basic equation, that is stress is equal to force divided by area. Now, if you are going to put these values, circumference of hub is given by pi d. Okay, d where d is capital D, that is the diameter, outer diameter of hub. Thickness of flange is denoted by T suffix F. Allowable shear stress in flange is given by tau C. Okay, and radius of hub is capital D divided by 2. From this equation, we can check whether this is capable to transmit the torque which we want to transmit. Okay, and from this we can check, from this equation we can check TF, that is the thickness of flange. Okay, and normally we are going to take it as a 0.5 of D, but if the allowable stresses are more, or the stress value which we are going to calculate is more, then we have to modify this TF. Got it? It is mentioned here. Any question? If not, we are going to go for next design, that is design of bolts. Now these all bolts are undergoing for the shear because one coupling is connected to the another coupling, and if one coupling is rotating and another is not ready to rotate, then all load is going to come on bolts and this bolt will get shear out. Okay, and we have to check whether that bolts are capable to sustain that shear stress or not, right? And they are not single, they are in group, how many number of bolts which are used. So let us, we have already considered that n are the number of bolts which are used. Capital D1 is the diameter of the hub, outer diameter of the hub. Okay. Sorry, pitch circle diameter where we have considered pitch circle diameter of the bolts, that is capital D1. Now at this D1, total force is applied. From here I will take this diagram. Here. Now we are calculating this center line to this center line, how much force is applied. Now force is nothing but torque divided by this radius. Am I right? That much force will get applied perpendicular to this slide to shear out that bolts. Right? So we are going to calculate first of all how much force is generated here by means of the torque. So load on each bolt is pi by 4 d square, that is diameter of the bolt square, into allowable shear stress of that bolt. That we have calculated because load divided by this area is equal to shear stress. Basic equation again same, stress is equal to force divided by area. Okay, so this area we are going to take to the other side, and load, that is nothing but the force which is responsible for shear, is equal to area multiplied by stress. Now the total load on all bolts, this is we have calculated for the single bolt. We are going to calculate for total bolt, and that will be equal to single multiplied by number of bolts which are used, n. Now torque which is transmitted by means of all these bolts, that will be calculated as torque divided by radius. This is nothing but this radius, this radius is the force which is applied to shear off. Okay, so this radius, torque divided by this radius. I am going to take this radius to the other side, it will become multiplication, that is d1 pitch diameter of that bolt divided by 2, that is the radius. Okay, and this is the force which is transmitted by means of all bolts, that will become the torque transmitted by means of all bolts. Got it? From this we can check the bolt diameter, because d1 already we are going to take from standard value, that is thrice of the shaft diameter, and d1, that is small d1, can be calculated because already torque which is transmitted, that we have calculated. Next, the area which we are going to consider for the crushing of single bolt, but we are going to check whether it is sustaining crush or crushing stress or not. Okay, so n multiplied by d1 multiplied by tf, tf is nothing but the thickness of flange, that will be the area which is undergoing for the crushing stress, compressive type of stress. Okay, so this crushing strength of all bolts can be calculated as n multiplied by d1 multiplied by tf into sigma c, that is stress is equal to force divided by area. Okay, and hence this force multiplied by radius is going to become torque as force. That's why if you are going to calculate force, this torque divided by a radius is the force. So torque divided by D1, that is pitch circle diameter of bolt, divided by 2, that is radius. Torque divided by radius will become equal to force. So this radius I'm going to take on this side. So that will become the total torque which is transmitted, and that is under the crushing or compressive type of stresses. By means of this, we can check the diameter of bolt D1 which we have calculated is safe under the crushing stress or not. If it is not safe, if the torque transmitted is not coming equal to torque which you want to transmit, then we have to go for the redesigning. We have to go for the again taking the diameter of this bolt as a different diameter which we are going to calculate here. Okay. Here we have finished this unit. Now we are going to take one example, okay, in continuance of this lecture only, okay, because my again next lecture is of mine only. Shall we go? Hello? Can we continue? Hello? Am I audible? Can we continue this lecture? You can write in text. lecture झालं की तुला कॉल करतो. Hello? Okay. We'll take or we'll continue this lecture till we finish this unit. Okay. So here the statement is given as design a cast iron protective type of flange coupling, okay, to transmit 15 kilowatt power at 900 rpm from an electrical motor to compressor. Okay, the service factor may be assumed as a 1.35. Now where to use this service factor, that we will see later on when we are going to calculate the dimensions. The following permissible stresses may be used: shear stress for the shaft, bolt and key material is 40 megapascal. Then crushing stress for the bolt and key is 80 megapascal. Shear stress for the cast iron, that is for the flange and hub of that flange coupling, is taken as 8 megapascal. Okay. Now these values which are given, power to be transmitted is 15 kilowatt, that is nothing but 15 into 10 raised to 3 watt. Speed is 900 rpm, service factor is 1.35. Then allowable shear stress in shaft, then bolt and key is 40 megapascal, that is nothing but 14 Newton per millimeter square. Allowable crushing stress in bolt and key is 80 megapascal, that is 80 Newton per millimeter square. Allowable shear stress in coupling material is 8 megapascal, that is 8 Newton per millimeter square. Now first of all, we'll design hub. Now hub, before going to calculate the hub dimensions, we have to calculate how much torque, because power is given and speed is given. So torque is given by P into 60 divided by 2 pi n. P is 15 into 10 raised to 3 and RPM is 900. So torque we are getting as a 159.13 Newton meter. We have to convert it into millimeter. Into 10 raised to 3, that will become Newton millimeter. Okay. Now, as the service factor is taken as a 1.35, that's why we have to multiply by this torque by means of this service factor. Okay, it is additional power that we can say as a design torque, that is maximum torque which that coupling should transmit. Okay, somebody's yes sir. 3 minutes before you told me that can we take break of 5 minutes? Yes, we can take break of 5 minutes if everybody is saying. Please be relaxed. I will take break of 5 minutes. Is it fine? Yes sir.
Yes, sir.
Okay, we'll take break of 5 minutes and we'll continue. Can we continue?
Yes.
32. Okay. There was 39 students. Now 33 are present. And today our presenting is compulsory. Okay. Shall we wait for that 3-4 students, or can we continue? Just will wait a minute. Those who are left. Okay, continue. Now, as in this problem, service factor is given. That's why the maximum torque which that shaft or that coupling has to be transmit, that should be 0.35 times more than the torque which is transmitted as a regular torque. Okay, so we have to multiply it by 1.25 or 1.35 with the torque which we have calculated. So 1.35 into 159.13 is equal to 215 Newton meter. Now this 215 Newton meter is converted into Newton millimeter by means of multiplying it with 10 raised to 3. Now this is the total torque, maximum torque that coupling has to be transmitted. Now this torque we are going to take for the calculation. Now this 15 into 10 raised to 3, we are going to calculate the torque which is transmitted by means of shaft. Now shaft diameter is calculated as pi by 16 allowable shear stress in shaft multiplied by diameter of shaft cube. From this we can calculate diameter of shaft, and it is coming as a 30.1 millimeter. Now this 30.1 millimeter is approximated to 35 millimeter. So 35 millimeter is the diameter of shaft on which couplings or flanges are mounted. Next, once you calculate the diameter of that shaft, then we are going to take diameter of the hub. Now this diameter of hub is the twice of the diameter of shaft. That's why 2 into 35, that is 70 millimeter, is the outer diameter of hub. Inner diameter of hub will be as the diameter of shaft, that is 35 millimeter. And length of hub is 1.5 times of the diameter of shaft. So it is 1.5 into 35, that is 52.5 millimeter. Okay, so dimensions of hub we have calculated. Now just we have to check that whether this hub is capable to transmit the calculated torque, that is maximum torque. So by considering it as a hollow shaft, hollow part, we are going to calculate the allowable stresses. So it is maximum torque is equal to pi by 16 allowable shear stress into bracket capital D raised to 4 minus small d raised to 4 divided by capital D. Okay. From this equation, we can calculate the allowable shear stress for the coupling. And this allowable shear stress value we have calculated as 215 into 10 raised to 3 divided by 63,147. Okay, and E is coming as a 3.4 Newton per millimeter square. That is 3.4 megapascal. And this allowable shear stress in this hub material is 8 megapascal. That's why our design is safe. This is allowable shear stress, and our calculated shear stress is 3.4 megapascal. Hence, the dimensions which we have calculated for the hub are safe. Okay. Once you calculate the dimension for the hub, next we have to design key. Key by means of which this flange or hub is coupled with the shaft. Okay. So we can take the square key where crushing stress in the key is twice of the shear stress. Okay. In that case, if we calculate the dimension, that is width is considered as a 15. Again, we can take it from the standardization. Okay, standard table will be provided to you, or we can use this empirical relationship and we can calculate the width. Okay, because allowable shear stress is given in that key material, as well as allowable crushing stress is given in that key material. So that can be calculated by considering the torque is equal to L, length of that key, multiplied by width of that key, into allowable shear stress in that key, into D by 2, that is diameter of shaft divided by 2. Because we are going to mount this key on the periphery of that shaft. That's why basically we are going to calculate the force, that is torque divided by radius. Radius from to the other side will become multiplication. So LW that we are going to calculate, L can be taken from the standard, that is L is equal to the length of that hub, and that we have calculated just now as a 52.5 millimeter. Okay, so L will be there. W can be calculated from this equation, or you can take standard W that we have here taken as a 12. Okay, thickness is also taken as a 12, that is square key is used, and we can calculate the shear stress, allowable shear stress value in the key. So it will become 19.5 megapascal, and allowable is more than that. Okay. Now, if we are going to, this is for the shear stress. If we consider the crushing stress, this equation will become L into T by 2. T is nothing but W again. That is W, that is 12 millimeter. Okay, 12 by 2, and allowable crushing stress into shaft diameter divided by 2. So that we are going to get this value as a 39 megapascal. So this shear stress which is allowed for the 4T in our problem, and crushing stress which is allowed up to 80 megapascal. That's why the dimensions of key which we have taken as a 12 millimeter width and 12 millimeter thickness and 52.5 millimeter length are safe. Any question? Next, we are going to design the flange. A flange is designed to take the torque at periphery, right? So first of all, we will calculate thickness of flange is equal to 0.5 of shaft diameter and is 17.5 millimeter. Then we are going to calculate the allowable stress. Okay. So here the torque which is transmitted is nothing but pi by 2 or pi into d actually here. Okay. So pi d square divided by 2 into sigma c, that is crushing stress, into thickness of that flange. What is it actually? It is a periphery. So I will elaborate this equation. This equation is T divided by R, that is force is equal to stress into area, shear stress into area, peripheral area is pi into d. Hello? This is basic equation, that is stress is equal to force divided by area. Okay, area again is periphery multiplied by thickness T suffix here, that is the thickness of flange. Okay, so area multiplied by stress is equal to force. Now this R we are going to take to this side, that will become d by 2. So this d and the R which we are going to take to this side will become d square divided by 2, right, into pi into shear stress in coupling into thickness of that flange. So that's why this equation has written. From this, if we calculate the allowable shear stress, it is coming as a 1.6 megapascal, and allowed shear stress is 8 megapascal. That's why the dimensions which were calculated, that is thickness of flange and the diameter of that hub, are set. Next, we are going to design the bolts which are used. Now diameter is below 35 millimeter. It is 35 millimeter of that shaft and it is below. That's why we are going to consider that 3 bolts are sufficient for that coupling. Now this D suffix 1, small d1, we are going to consider as a normal diameter of bolts. Okay. Capital D1 we are going to consider as a pitch circle diameter on which bolts are mounted, and it is taken as a thrice of shaft diameter. So it is 105 millimeter. So bolt is subjected for the shearing. So maximum torque, again from the same equation, okay, torque is equal to pi by 4 d small d1 square, that is area, multiplied by stress into number of bolts which are used, because this torque, all torque is sustained by this total number of bolts, 3 number of bolts, into radius of at which the bolts are mounted. So this torque, if you are going to take this side, this force is equal to area multiplied by stress. Okay. So this equation, if you are going to solve, then small d1 is coming as a 6.6 millimeter. So from here we can take the diameter of bolt and we'll compare it with the standard one. 6.6 millimeter is not the standard diameter of the bolt. Smallest size or bigger size available is M8, where 8 is the normal diameter of that bolt, 8 millimeter. Okay, so we are going to take this M8 bolts and we are going to use it for the flange coupling. Okay, now outer diameter of the flange is denoted by d suffix 2 and it is 4 times of the shaft diameter. So it is coming as a 140 millimeter. Okay, and thickness of the protective type centrifugal flange, okay, that's TP we have denoted it, taken as a 0.25 of D or 0.5 of the D. Anyone here we can take 0.5 of the D. Okay, and that is coming equal to value of TF. TF is how much? Already we have calculated it. 17.5 millimeter. and can be approximated to 20 millimeter. Okay. Any question? If not, we are going to stop here, and we have completed this unit number 4. Okay, from the second section. Now I'm going to take presentee. This presentee I have to give to CC right now. Today is 26th. I'll take present. Any question before I'm going to take presentee? While I'm going to take presentee, let me know if you do any question.
No, sir.
Yes. What? Any query? Yes, sir.
No, sir.
Yes. So, do you have any query? Huh?
No, sir.
No. Okay.